Welcome to another series on electric motors. As you know, in our previous series, we have looked at the type of motors we have in the market today. That is, synchronous motors, asynchronous motors, servo motors, and DC motors. The torque-to-speed ratio of these motors was looked at. Finally, we ended off looking at the major difference between concentrated and distributed winding. In today's series, we will be looking at how electric motors are wound. The techniques that are commonly used during coil terminations will be looked at in detail. So without any further ado, let's get started. I believe we all know that when an alternating current is applied to a conductor, magnetic field will be generated around the conductor as current flows through this conductor. Now, because we are dealing with an electric motor, the conductor is usually wound in a coil form. And as such, another magnetic field will be generated. The second generated magnetic field will rotate in the opposite direction to the first one. That is because of the direction of the flowing alternating current.
It is very important to note that the direction of the generated magnetic field can be known by using a right-hand thumb rule.
Of course. When a current-carrying conductor is imagined to be held in your right hand, and such that the thumb points along the direction of the current, then the direction of the wrapped fingers will give the direction of magnetic field lines.
Now, this generated field is what we want to manipulate to generate a rotating piece. So when the coils are arranged in a special way, then continuous axial rotation can be generated.
Now, let's leverage on the already established fact. That is, using the generated rotating magnetic field to cause the rotor to move, and to continually move.
Now we will place a conductor to this Pharma here. It is important to note that this equipment is used to create a tight and evenly wound coils of multiple turns.
Again, it is also important to note that the number of turns will determine the magnitude of the generated magnetic field. So in a layman's terms, more turns will equate to a greater generated magnetic field or force.
Of course, to be able to move a rotor of a certain weight, then it is important that the generated magnetic field must be adequate enough before the rotor will be able to move from rest to its rated speed.
Perfect. Also, Laura, it is very important to look at these data so that we can fully understand the motor parameters. The motor we have here is rated as a 3-phase motor that operates at 50 Hz. The 6-coil terminal is connected in star configurations. The stator of the motor is slotted in 24 ways, and with 10 conductors per slot. The flux per pole is 0.03 Weber and the speed is rated 1,500 revolutions per minute. Now with these data, we can calculate the number of poles of the motor, the slot per phase, the total stator conductor per phase, and the number of turns per phase. So using the synchronous formula, and when our frequency is 50 Hz, then the number of poles is 4 poles. Also in slot per phase, it is equal to the total stator slot divided by the number of phases. Hence, this means that we will be having 8 slots per phase. Also, The number of stator conductors per phase is equal to 80 stator conductors per phase. And finally, the total number of turns per phase is equal to 40 turns per face.
It is of great importance to note that the number of turns for each phase must be even. Otherwise, it will result in varying current flowing in the motor's three phases, and the motor will be unbalanced. The operation of the motor will not also be smooth.
Again, in a situation where the turns are not equal, the generated magnetic flux will not be equal. The rotor rotation will not be as expected, which is because the force acting on the coil is not even. The motor will generate a warbling sound, and heat will also be generated as a result.
As a result of the uneven turn count, the expected lifespan of the machine will be less. That is, the motor will degrade quickly and the expected speed will not be reached at all times during the motor operation.
Also, looking at this graph here, on the right is the expected RMF shape and on the left is the RMF of a motor with uneven turns. This happens because the flux with north and south capabilities has uneven turns. Hence the reason. For a smooth rotor rotation, it is important that the turn should be even. Again, the ohmic value will not also be equal. This will be discussed in a moment.
Now Andrea, take this wound coil and slot it in the stator slot. Again, the total turns of this coil are equal to the calculated parameter that was discussed earlier, which is the total number of turns per phase is equal to 40 turns per phase.
So we now have 3 winding of 40 turns each. Now let me connect all the terminals in a star configuration and let's see.
The rotor rotation is not acceptable. The rotation seem to tends to 0 at a certain instance. Also graphically, the generated field is not smooth when we look at it at glance.
The reason why we have an irregular rotor rotation and the not-so-smooth generated field is because the current pulsation, be it at maximum or at minimum, happens at the same instance for all the 3 phases. That is, all the phases generate a magnetic flux that has north characteristics at the same instance and vice versa. So the rotation will not be smooth and regular.
In order to produce a fully rotating magnetic field, the current pulsation, be it at maximum, should be kept at different instances. With these, all the 3-phase currents will not be at maximum and 0 at the same time. Instead, when the magnetic field that is acting on the rotor is about tending to 0, the current of the other phase will be at maximum. And thus, the rotor rotation will always be constant and uniform motion can be achieved.
This current arrangement won't have been possible without Nikola Tesla. Tesla was the one that come up with the idea that when the current pulsation is arranged at different instances, the coil will produce a rotating magnetic field, and as such, the rotor will continue to rotate as long as the field is energized.
Now when we look at this graph here, the generated field is uniform and it does not tend to 0. This means the rotor will continue to rotate without always tending to 0.
So the motor that we have now can be known as an electric motor with 2 poles. And that is after Andrea has installed the wound coil to the stator slot. And it is for this reason that the generated flux is not smooth enough and it is also not consistent. That is because of less number of poles.
At this moment, we have only adhered to the number of turns, not the number of calculated poles. Hence the reasons for the irregular rotor rotation.
It is also important to note that a motor with few poles tends to generate a higher rotating speed. But the tendency to slip out of synchronization with the generated magnetic field is very high when connected to a varying load.
Perfect. Because this winding is a little bit far from the other windings. So the rotor will tend to quickly move to the next slot with the energized windings. So as the rotor moves. And also because the winding is a little bit remote and when it is suddenly connected to a load. The probability that it will slip away from the rotating magnetic field is high. This is because of the less number of poles. This phenomenon can be known as a motor with less torque but more speed.
Now, Andrea, please add the remaining coils to the stator slot.
Now for the U phase. The coils will be connected like this. Slot 1 and 6. Slot 7 and 12. Slot 13 and 18. And slot 19 and 24. For the V phase, the coils will be connected like this. From slot 5 and 10, slot 11 and 16, slot 17 and 22, and slot 23 and slot 4. For the W phase, the coil will be connected like this. From slot 19 and 14, slot 15 and 20, slot 21 and 2, and slot 3 and 8. Now that is the arrangement. The next thing is to terminate the start and the end of all the coils in each phase. So the end of the first coil will be connected to the end of the second coil. The start of the second coil to the start of the third coil. And the end of the third coil to the end of the fourth coil. The remaining coil will be connected to the motor terminals. The same connections will be repeated for the other two phases.
These connections and coil arrangement will produce a smooth rotating magnetic field on all the windings. This will cause the rotor to rotate smoothly.
Also earlier on, I made mention of the ohmic resistance of the motor. Now since we are having a motor that has the same number of turns across all the winding, the ohmic resistance of each winding can be gotten using this multimeter here. The value gotten is 0.166 kilo ohm. The ohmic tolerance value for each winding should not be more than 0.5 ohms. That means if we have an ohmic value of 0.167 kilo ohms, then it's still acceptable.
So there you have it, guys. This is a 1.5 kilowatt motor with a 24-slotted stator. The speed of the motor is 1,500 revolutions per minute when connected to a main of 400 volt. At 50 Hz power supply.
With the listed parameters, the current rating of this motor can be calculated in different configurations. Assuming that our power factor is 0.9. So when the motor is connected in a star configuration, the current drawn would be 2.4 amps. While in delta configurations, the current drawn would be 4.1 amps. So when connected in delta, the current drawn will be a little bit higher than when it is connected in star configuration. The circuit breaker rating that will be needed for this motor should be above 5 amps or above when using this calculation here. It is on this note that we will be looking at motor starters in the next series. That is direct online starter, star delta starters, sequence starters, and to mention a few. Hope you have learned something new today. See you at the next one.